Hey folks, so like to introduce Anna. She's joining us right now, and also, well, I guess uh, I heard she was having some technical issues logging in. So if Anna needs a minute or two, I can actually go back and kind of do
I'm
a quick.
here. Can you
All
hear
right.
me?
Yep. Hear you just fine. Everything's working well on your end.
Can you see me?
Oh, perfectly. Yes.
Can you see my rooster?
I like the rooster. Actually, it has no head.
Oh,
There we go. Perfect. Well, so introducing Anna, really, Anna's bio is incredibly long. That's also because you're really accomplished too. I had no idea. Really, you've got over 15 years of teaching experience. You've been working as the stats consultant for about 13 years, and really, this is one of the reasons I came to you at the conference. And I really want to go through and get stronger on my statistical skills. And it was great, and it was such a great conversation we had. Meeting you was fantastic, but I'm like, you should really come on to the Fringe Festival and share some of this knowledge. Anna's also a technical training director now, and this is kind of what you do now full time, right?
yeah, I do. I'm on the training side of our company where we train Tableau, but also statistics. And I also help train trainers and hire trainers to get them up to speed so they can train these awesome clients of ours who need these technical skills.
Excellent. Well, without any further ado, I will leave you with Anna, and also from the Tableau Data Pane to Predictive Analytics Basics. It's a long title. All right.
Yeah, I should have shortened it, but I went, So Caesar, by the way, is fantastic to talk to, not just about, stats and Tableau, but he's got some good ghost stories to tell you. Yeah, ask him about it sometime. The best stories. So I enjoyed, but the last two Tableau conferences talking to you, that was so much fun.
No ghost stories this year, so
I was bummed.
I might have some next year. Let's see.
We had some good jokes, though. That was fun.
Oh yeah, definitely.
So I am going to share my screen, correct? And get us started. And so you guys can see, oops, here we go, my Tableau residual chart and also the start of my presentation. So here we go. Do I need to close this thing? Probably best. All right, y'all. So really quickly, just big overview of what we're talking about today is this idea of predictive analytics is just inundated our world. People talk about predictive analytics and sure, heads nod, and yeah, what is it? And it actually started in your math classroom. You learned about some of this a long time ago, and I think the way that the math, I could go on a tangent here and talk about the math curriculum and how we just pack so much in and shove it down your throat, and then you're like, see, I have fun with that. And so I'm going to slow it down a little bit and just give you this high level of how trend lines work and how you would assess them, and actually how you would communicate their meaning to someone else, and attach this back to things that you learned a very long time ago, or I don't mean to assume, or just a short time ago, for those of you who just graduated. And I hope this helps, but feel free to ask questions. I'll have a couple interactive sessions, but if you have a question and you want to put that in the chat, I can get back to that in a little bit. So 3 points I just want to make today is when we're going to use trend lines in a visualization. There actually is a reason you wouldn't. There's a lot of reasons you wouldn't. How to assess that model. And then we're going to build something called a residual plot in Tableau that's going to help us assess that model and like, is this worthwhile or not? So to get us started, I will kind of give you a little bit of my background. Honestly, Caesar already said it. My undergrad was marketing because I had no idea what to do. And by the way, can I stop for a second? How do I make this go away? Is there a way to do that? I'm not sure. Okay, sorry about that. So my undergrad was marketing because I had no idea what I wanted to do with my life. And so with the background that I had with I took business classes and just decided, okay, I'll go marketing. I really enjoyed economics and finance and real estate and marketing and all of them, and I just had to pick one. So that's really like where I started. I did enjoy math and I did enjoy statistics. So with that, with that, I just decided marketing would be the best bet for me because I can apply some of this. So when I started when I graduated college, I went to DC and I worked for this company called Corporate Executive Board, where we worked with best practices research. And in this research, what we were doing at the time wasn't common. We were working with analytics, and that wasn't actually a thing at the moment. We were working with models to figure out people in different departments of a company, for example, like what was their incentive for going to work. And it was just kind of interesting, but we were modeling these ideas or these incentives for people who, how would we want to retain these people and then give this information as a report back to HR departments. So I started with that and actually went back to school to be a teacher. Not long after that, I wanted to teach math and statistics, and that's actually my assistantship had to do with statistics curriculum. And long story short, taught high school for 14 years. AP statistics was the main course I taught, but along with, geometry, algebra, pre-calculus, all of them. And after teaching AP stats and seeing that these kids were not going to go into a corporate world with a TI-84 calculator, but they did need to know how to use Excel. I started using Excel and then eventually Tableau. So here I am. I did also help teachers when teachers were working with their dissertation and having to defend the stats of their dissertation, I would coach them through what those statistics meant and how to defend them. And that just gave me that ability to get some side income, but also kind of put me where I am now, where I help people just communicate those insights. So on to what I like to do. I like to do really weird things. If you know me, you know that I just am like, hey, sure, I'll do something weird. So last week I started rock climbing. Just beginning of last week, I said, I'm going to start. Now it's not real rocks, right? But eventually. And this is yesterday. I finally graduated from the auto belay to the real belay, and I got to the top of my first try. And I was like, I want to show everyone this picture because I was really excited. And then there's a lot of things I'm not good at, and one of them is design. So you guys in the Tableau community help me out with the things that I am really not good at, because stats is my thing, design not so much. So thank you guys for helping me out. So on to trendline basics. We have this knack for being able to use this self-service analytics to just create an answer. And we use it sometimes haphazardly, not realizing if this is useful or not. So that is, of course, the scope of this talk and when we can use it. I love this picture. This is actually, I had to cut off the bottom part of this comic because I couldn't fit and you wouldn't be able to enjoy it as much. But basically, you get the idea. They're fitting, curve fitting with linear and nonlinear models. And actually, all of these are linear models, except for the loss. They are looking for this best fit of this data. And if you really look closely at this comic, and if you look at the black dots and just ignore the red in every single one, you'll notice that they're all the same. However, if you look at the red lines or curves, you'll notice your eyes go to whatever it's telling you. Meaning, if you put a regression line or a trend line into your visualization, you are telling someone where to look. And that can be awesome, but it can also be very, very misleading. So that's one of my warnings when I go through this. I did this with Superstore data. I throw that line in there like, hey, as discounts increase, our sales go down. Maybe we shouldn't be discounting. And of course, that is made up because I just threw a line in there that doesn't match anything. Tableau and also other analytics software were spit out this information and we're like, hey, low p-value, let's go with it. And I'm here to warn you, well, maybe pause, just pause, and I'll help you out to explain to somebody else why you would. And then I found this on the interwebs. I thought that was interesting because, again, the red line makes you think there's a relationship, but if you look at just the dots, it says to me that they just plotted something and they made a scatter plot. So we have two reasons for trend lines. We want to emphasize a relationship. Like I said, that line helps you know where to look. It tells someone where to look. And also the other thing it does is helps us make predictions, which is why I said this is a little bit of a step towards predictive analytics. This is your basic baseline of predictive analytics. So I'm also here to tell you, as I said, communication is so important to me. And what I do when I teach and when I train people not on the functionality of the tool. I teach people how to explain what you are doing and how to ask questions, then how to take those insights and those answers to somebody else. How do you explain that to somebody else in the simplest terms in context? When I taught AP statistics, and I'll be honest, I will tell you a lot of what I learned is from teaching, and I can't get away from that. So when I taught AP statistics, I can tell you on the AP exam, and I think this is where this test gets it right. I'm not going to always say a test gets it right, but what they do on grading this test is you can get the number wrong. You can actually do a calculation and calculate the wrong number. However, if you can explain its meaning in context and explain it in a way that somebody else can digest it, you get most of your points. You can get a 5 on the AP exam if you can communicate. And I feel like that's so important for everybody to be able to communicate what all of this means. So that's what I'm going to help you with today. So that's why I'm going to start with I took some personal data and I decided to use that instead of Superstore data. I was hoping some people can attach to this. I know we all don't. But a few years ago, I was looking for a car. I was actually looking for used 4Runner. And I started looking at, prices. And I don't know if you've ever looked for a used car before, but one of the first things you look at are the number of miles on the odometer. And I know it's not like a one-to-one relationship, like, hey, for every mile, you're going to pay this $5 less. It doesn't work that way, but there's a relationship. So I decided to just get some data, gather my own data, and find out if you can predict the vehicle price from odometer miles. Okay, so when I teach predictive analytics, when I talk about being able to predict one from another, it's really important which variable is on your x-axis and which is on your y. And I realized that that's not universal, that not everybody knows that, because again, when you were taught this in high school or college, they run right through it and take a test, see you later. So I'm going to take a second to tell you that your x variable, that's your x-axis, there at the bottom, is going to be your input, if you want to think about it that way, your independent variable. And then the y is your output, your dependent. So if you want to predict, whatever the output is what you're predicting. The input is what you're predicting from. So if you're predicting vehicle price from odometer miles, your x variable would be the mileage, how many miles are on the vehicle, and the y is that price. How much did it cost? Because that's what I want to predict. So that's really, really important thing to start with, is just these basics of, okay, well, where do I put what? If you switch the two, it wouldn't tell the same story. I'll get to that a little later. All right. So I can tell you this is not a random sample. I went to autotrader.com. I found 3 non-random cities, and that's actually important. How you collect samples are quite important. I went to 3 non-random cities, found probably the first X number of vehicles on there, and just plotted those. So this data is not random. This is not from one city, but it is real data from AutoTrader. And what these dots represent is a different forerunner. And if you see at the bottom, we have those odometer miles, and on the side, the price. Now, plug that into Tableau, and you are going to get some output. So I'm going to switch my screen to Tableau, if it'll let me. There we go. And show you exactly what I'm talking about. And I'm going to take this off. Let's see. All right. So here we go. I went ahead and put my odometer miles on my columns because that's my X, and price on my rows. And then I brought into my detail which forerunner was there so I could have all of them here. So what I'm going to do now is switch to the analytics tab to find trend line. And it's really easy to do. And that's why I warn you, make sure you know what you're doing when you're bringing in a trend line. So it turns into a gray pill. So we're just going to drop it in, and you'll notice you have all these options. I'm going to choose linear. I do want to point out, and this is not in the scope of this talk, I want to point out that every single other one of these are also a type of linear model. These are all linear. I know they look curved, but they do. There's a transformation with logarithms and exponents. There's some math. Look, if you want to talk about it, you can hit me up. I can tell you how these are all linear on another time. We're just going to take linear model, drop it in there, and we can hover. And I think what a lot of people like to do is go, hey, the p-value is less than 0.05 because that's what we've always heard. We're good to go. This is a good model. And I will tell you that the p-value is a sniff test. I'll get to that later, but I actually really want to look at the R-squared value. This R-squared value is going to give me a little bit more insight on what's going on. So let's talk about what is R-squared. First of all, it's not correlation. When I teach, I like to tell people, okay, this is what it is, and this is what it's not. That way you can kind of see, okay, I assumed those were the same thing. Let's figure out why they're different. So taking a step back, again, I know I'm going correlate R-squared, but this is all about reviewing those concepts that you learned before. Correlation is this word that we use on when we think two things are related. In fact, you might hear something like somebody's IQ is correlated to their hair color, which I can tell you, first of all, is not true. But second of all, it can never be true because hair color is not a quantitative variable. Aha, got you there. So let's see what correlation really is. This is Carl Pearson. He is the person who the Pearson's R is named after. He really didn't make it up, but we won't go into that. What does correlation measure? It measures the strength, the direction of a linear model, of a linear relationship in quantitative data. So basically, how strong is this relationship? Is it going up or down? As one increase, does the other increase, or does it decrease? And then correlation only works with linear data. So if it's nonlinear, meaning we have curved data, we either have to transform it into linear data, which I told you that's kind of another math story for another day, or we can't use correlation. That's interesting piece of information for a lot of people when we try to use the word correlation sometimes. It's fine to use the word, but make sure you're not putting a number with it. So it has to be quantitative data, and Pearson's R, this value, is actually the square root of R-squared. So that's why I say, well, what's R-squared? Let's start with R. That output that you get, you'll get R-squared all the time, and R-squared is really, really important. But if you take the square root of it, you'll get correlation. It's either going to be a positive or a negative number. Thank your math teacher if you remember that when you take a square root, you actually have a positive or a negative. So it can actually be either one, so you have to pay attention to the relationship. And it's not this binary like, hey, it's strong or weak. It's on this continuum of, well, it could be strong, it could be weak. I'm going to show you another example here. I love this because then I pulled this from like Wikipedia, I think. Because it shows us the linear relationships in the middle where it doesn't matter what the slope is, which, you know, kind of it's more steep, less steep. It can be +1 if it makes a straight line. In the middle, you'll see a horizontal line. That's that's a slope. That's a slope of 0. And actually, that, can you see there's no correlation there? Like, it's not. There's importance there. Actually, that ties back to p-value. The fact that there's no number here is actually super important. So we'll come back to that. And then up here at the top, you'll see when our scatter plots start to look a little bit more like just a fuzzy mess. That is where our correlation starts to get weaker and weaker and weaker, and that's where we start to get closer to 0. And then at the bottom, you see, hey, those make shapes. There's a relationship between those variables. But why is the correlation 0? Well, the correlation 0, yeah, there's a relationship, but there's not a correlation because it's not linear. So just some recap here with R. And again, R is not R squared. So what I did is I took the square root of this value, and I got 0.8949, but then I said, oh wait, as odometer miles goes up, the price comes down, so this is actually negative. All right, so I have a little interactive session for you right here, and I don't have a second screen, and I should have mentioned that, so I'll have to figure out how to do this, but there's this interactive, and maybe you can help me out, Caesar. If you know which correlation here on the right is A, well, actually we have A, B, C, or D. I have more correlations on the left here than I have scatter plots. So you can imagine I'm that teacher. Yeah, it's going to be like that. If you can figure out what you think A is, if you could put in the number, that'd be great. I will tell you, if you need a hint, I would start with the easiest ones because A might not be it, and then go from there. I'll give you a second.
I'm going to call out really fast. Rodrigo already shot out. -1 is D. And Will is also shooting out. -1 is D.
Yep, you're right. You got that one. Hey, Will. Good job.
Neil is saying that A is -0.17. Will saying B is 0.17.
Interesting. I will say that Neil is right.
Yeah. Paul is agreeing with Neil.
Yeah, Neil's right. Yeah. Okay. So far, nobody's gotten B right.
Ooh, all right, all right.
Yeah.
Will is saying B is 0.17. Let's see. Paul is agreeing with Neil. Will is now saying that, well, he's now answering for C. C is 0.82.
C is 0.82. Mm-hmm.
Neil has activated smug mode.
That's awesome. And then B is a tricky one. So I'm going to tell you that.
Rodrigo and Danielle right now are shooting in answers for B. So 0.17 and 0.82. Both coming in for B. 17 is coming in from Rodrigo, and Danielle is shooting in a 0.82 for B.
So I put B in here. By the way, when I had this on one of my tests back in the day, and people don't get B right very often. And I bring this up because it's a big warning. When we have data points that are all collected in a corner, like you see in B, and then you have one very far away, the way that the calculation works, and I'm not going to get into the math, the way the calculation works actually starts to treat, if this, and I'm going to use my cursor here, if this outlier is far enough away from these, if it was close, it wouldn't work this way, but if it's far enough away, it actually starts, the calculation will start treating these four as one point, making this look very, very strong. This is actually a very strong correlation. And if you didn't look at the picture, you would be like, wow, that's a really strong correlation. These two things must be related. And looking at the picture, they don't look related at all, which you're right by saying they're not related. That's why we look at the picture. That's why we visualize. But the answer to B is, did anyone have another guess? Because I haven't heard it yet. Sarah
has thrown in a 0.98 for B.
That is correct. B is actually 0.98.
Yeah. Okay, yeah, Neil's also saying, well, 0.98 then for B as well, and Will as well. So, yeah.
Hey, we got it. Yeah, and hopefully that helps you with our understanding of why we visualize too, because if you just look at correlation, it can be very misleading, right?
Yes. Will is saying, dang you and your stats.
I love you too, Will. Awesome. All right, so I'm going to move right along here, and I will have this workbook that I'm going to have. I'm going to have it on my public. I meant to have it earlier, and it just didn't work out. So there's that. But I'll have that on my Tableau public this afternoon. So R-squared. Well, what is it? The one way to explain something that's a little complicated is, and this is a complicated concept, is to actually first start with, well, what's a perfect world going to look like? R-squared is a number. It actually gives you the decimal form in Tableau, and most software does, but it's actually expresses a percent or fraction, and usually I'll talk it as a percent. So I'm going to start with what 100% would look like. I did borrow this example from another AP Stats teacher, which again, I have to always go back to teaching when I teach. So like all of the resources I've used, and since I taught high school kids and had to explain this for 14 years, I feel like this is the best way to give everybody a big idea of what's R-squared. So let's say you own a pizza place, and pizzas are $15. So this would be a cheese pizza, right? Like you got no toppings, except we're going to assume cheese because it's not a pizza without cheese. And starting with $15, and then each additional topping is $1. So if I were to show you a model of what this would look like, as I add a topping, every time I add a topping, the price goes up by, you guessed it, $1. Look at that beautiful line. And going back to algebra, we could create a linear equation to model this. That's your y equals mx plus b. If you remember, the m is your slope, your b is your y-intercept. And this is where you, I honestly think this was middle school where they started making you plot the dots and then draw the line. And that's actually where this starts. That's where this concept, where you learn this concept originally. And the model, I'm not going to go into what the regression does here, but here's the model of the line is just the model of what's going on to help you predict for more toppings. And you'll see R-squared is 1, and like as I said, it's expressed as a percent, so that's 100%. And I'll tell you what that means in just a minute. Slope, because this is a model and I want to talk about the whole thing, tells us for every additional topping we order, so that's the number, whatever number goes here is our slope. Excuse me, whatever goes here is our slope. For every additional topping order, the pizza price increases by $1. So as we input here, here's our X, our output is here, our Y. That is why it matters which is X and Y, by the way. So there is your slope. Your p-value, and that's also a topic for another day. This is, I would call this just a sniff test for your model. It does tell us the probability that this particular sample that we're dealing with is going to produce a slope this far away from 0 if the slope was actually 0. That's actually what that means. It actually has to do with the slope. And what the slope tells us is that relationship, as you know, as a price, a number of toppings goes up, the price goes up by $1. So if the slope was 0, there would be no relationship between the two. So p-value gives us a lot of information about the relationship between X and Y. Mathematically, there's a slight relationship between p-value and R-squared. There is a math, I can go into it on the side, not today. However, they're not related here. It actually has everything to do with context. So I think a lot of people think p-value and R-squared are telling the same story, and they can be telling the same story, but they can also have nothing to do with each other. I will say if the p-value is really high, and you know, a lot of people use like 0.05 as a sniff test. Just, you know, a high p-value, no matter what the R-squared is, if it's a high p-value, your model's trash. Like I'm just not even gonna, it's either you need a new sample, you need a larger sample, you need to ask some other questions, but that model, the R-squared is really not gonna be very valid if your p-value's high. I'm not gonna go into that right now, but all right. So what is R-squared? It's called the coefficient of determination. It's actually not the correlation coefficient. It is the coefficient of determination. It determines something. This is our sniff test of trendline predictability. And this is the part that I would have my AP Stats kids memorize. I'm like, okay, you have to just memorize this. You have to say, okay, this is the percent of variation in the price. In this case, it'd be in the price explained by the model relating price to topics. And after a while, I kind of memorized it at first, but then after you think about it, it makes sense. This is how much the y variable varies, in this case price, as you give the input of toppings. So, and another way to explain it is, I'm sorry, it's how much it can be explained by the x. So in this case, 100% of the price is explained by the number of toppings. Well, if you think about it, if it's $1 for every topping you put on it, it's just going to go up by $1 every time. There's no other variable that is impacting price, right? If there's no other variable impacting price, then R-squared has to be 100%, because toppings, the number of toppings, is the only variable impacting price. That's actually what that means. It's the percent of variation, how much the price is going to change based on the input of your x. 100% of the variation of pizza prices are explained by the number of toppings ordered. All right, that is a perfect world. It does not happen. It's not going to happen, because you know what? In the real world, there are multiple variables that you can or can't control for, some that you don't even know are out there that are impacting your model. And that's why R-squared is really, really important, because you need to understand how much of your model is impacted by the variable or variables that you are tracking. All right, I see that there's some Q&A, and I want to stop for a second, and Caesar, I'm gonna let you jump in there if you see anything important.
Awesome. What I see here is a quick question, or a question from an anonymous attendee. It says, on that point, does Tableau have the ability to do more complex regressions, adding in fixed effects, iteration effects, or multivariate models in general? Is the complexity based on dimensions or measures used?
Yeah, so no, not in Tableau's form, it does not. You'd have to bring in our and modeling outside of Tableau would have to be brought in. So no, it does not. There is, one thing I can do in Tableau is I can do simple analysis with correlation matrices, so I can look at the correlation and actually be able to look a little bit more at the R-squared of each one separately, but impacting together a multiple regression, as you will, I can't do that in Tableau. So, are there any other questions?
Great. No, we're clear right now for the Q&A section. Thanks.
Cool. Awesome. So this is fun, right? I love linear models. I think this is, I could talk all day about this. I'll try to keep it short though. This is kind of the next step now. So now what I'm going to do is add a layer of complexity. In the real world, we don't have a R-squared of 1 or 100%, because outside variables, as I said, impact our pizza price. And I'm showing you just a very, very simple example of that. In real world, the pizza price could also be impacted by somebody has a coupon. Your waitress who's new, she's only been on the job 2 days, dropped pizza in somebody's lap, so they had to comp it, all of those things. So we have to consider there are all outside variables. So I'm going to make this very simple by just adding another dimension, and by saying like, okay, well, what if there's multiple types of toppings, because I like my artichokes and my black olives. Well, I guess that's regular. I'm in my Italian world, we like to put on our premium toppings. So I want the $1.50 toppings, and I might put my black olives, my $1 toppings on there as well. So what does that model, what could that look like? And I just did some examples, putting in some possibilities here of the number of toppings that you would have, and the price. And then you'll notice that our model looks a little bit different. We still, have a linear model, and that line cuts straight through those dots. So, okay, well, maybe we can still use this for prediction. But let's look a little closer. Our p-value is less than 0.05, so yay, this is a good model. It just tells us there's a relationship. But R-squared is a little bit lower. R-squared here is telling us that 89% of the variation in these prices, in these pizza prices, can be explained by the number of toppings. So only 89, that's still high, by the way, but only 89%, meaning something else is changing the price of the toppings. And we all know what that is here. That's just going to be, in this situation, that's just going to be what type of topping they picked. So that variation you can see starts increasing up here as well. So I like Archer. I'm a big fan of Archer. So I had to bring this one in here because I'm like, okay, be careful. This is where you have to be careful, because R-squared doesn't mean the model is 89.2% accurate. And that's where we get into, it sounds like it's semantics, but it's a big deal. It looks like, oh, well, maybe it's 89% of the points is passing through. No, that's not what it means either. We need to recognize that it's just the percent of variation it can explain. The model is only as smart as what it feeds into you. Do you remember when your teacher would tell you that your calculator is as smart as your user? I had that teacher tell me that too. You know, you don't put the parentheses around the square root or the negative or something, and it tells you the wrong answer. Well, you forgot your parentheses. Well, here's the model only knows what you put in there. It actually has no idea what else is out there. So 10.7% of the variation in these prices has to be explained by other variables. This is where your common sense comes in, where you're like, well, clearly I know it has to do with the type of toppings. I created a waffle chart to show you this. 100%, this R-squared. R-squared will make up 100%, but just some of it's explained variation and some of it is not. And then, so I want to go back to the forerunners now, because this has definitely a little more variation, a lot of variables impacting price of a vehicle, not just odometer miles. So that's where I'm coming back to with R-squared is I'm hoping that you are digesting this a little bit and understanding that R-squared isn't just telling us, oh, this is a good model. It's telling us how much of our model can be explained by the input you put in there. All right, so 80.1% of the variation in forerunner prices are explained by the number of miles on the odometer, but almost 20% of the variation in forerunner prices are other variables. What other variables, this is where I stop, and we can also take some questions here. What other variables might impact the price of a vehicle? And I'll let Caesar navigate this one.
Right, so I'm getting a lot here. It's coming through on the chat.
Sure.
So Will is saying, well, is it a 4x4? Sarah's saying age. Will again with leather. Joe with condition. Will with color. Joe with color as well. Brand, condition, year from Danielle, and Yi with brand name as well. So a lot of different variables coming through.
Perfect. See, this is why I chose this as an example, because a lot of us can attach to purchasing something, doesn't have to be a vehicle, but purchasing something that is used, especially, and new as well. New will change, but odometer miles is something we look at when we purchase a new vehicle, or used vehicle, excuse me. And so I thought that this would be a really good example because we can bring in some other variables. And I know that if you've done enough research looking at vehicles, you might go, oh, hey, this is only 10K and it's only 80,000 miles on it. And I think enough of us know enough about vehicles to know, we got to question this. What's going on? Does it have an engine? Like, what's going on with this one?
Will's asking, does it smell?
Oh, I saw that Seinfeld episode.
or smoke. There's smoking never leaves the car.
Oh yeah, there was a Seinfeld episode where he like drops it off at the valet and he gets it back and it smells and no one will drive it. That's probably what it was right here. And what's interesting though, I do want to tell you this, what was interesting about the modeling of this particular vehicle, and I can't say this about other vehicles, and I'm not trying to sell you on a forerunner, but this actually, the price from a brand new vehicle was not much more than a vehicle with just like 10,000 miles. Basically, this particular vehicle holds its value pretty long. So I ended up just getting a new one. After doing all this research, I was like, I'm just going to get a new one because I got like a really good warranty. Are there any other questions?
No questions yet.
Cool.
There's a little bit of chatter about Will's previous career as a ballet. So
That's awesome.
going on.
You guys are the best. Man, this is fun. Thank you. Well, I do need to point out, though, this was a sample that I just haphazardly came up with to compare these prices. And as Bill Nye says, consider the following: that a different sample would produce a different R-squared value. That's actually the R-squared value is produced because of this sample. When we are working with data, and I'm not sure how much we think about this, but it's really, really important. When you're working with data, do you ever stop to think that this is just a subset? This is just a sample? You don't ever see the whole thing. You're never seeing the entire picture. You're only seeing a portion. And that's super important when trying to draw conclusions about the big picture, about seeing the whole thing. Because if you don't step back and look at it as a sample, and a different sample would produce a different outcome, then you might give somebody the wrong idea about your suggestion, because you don't want to say this will always happen. Well, this is actually happening now, but what's going to happen in a year? So that's important to point out. All right, so I like to give warnings. I don't say this as you're doing it wrong. I'm not trying to say, hey guys, I'm right, you're wrong. That's not what this is about. This is more of like, hey, how do we check to see if things are right? Because I just showed you how to look at R-squared. Well, it's a number, and it could be a little subjective. In fact, R-squared, like how high does R-squared have to be? Well, in behavioral sciences, when we're dealing with people, R-squared actually can be considered high and still be like in the 30s, because you can't predict human behavior. So that's really important to understand. So there's other things we have to look at to see if our prediction model is useful and worthwhile. So Ice Cube said it best, and well, there you go. This is also something I would tell my students to, like, check your work, just plug it back in and see if it works. Dude, Ice Cube would. I think he would. So we have another thing called residual plots. And a residual plot helps us look at prediction error. And this is an example of a residual plot, which I'll show you how to build that in Tableau. And it does include level of detail, very simple. And hopefully you'll learn something from that as well. But this residual plot shows us, what I've done is I plotted, here on the x-axis, you can't see it, but what I've plotted is, and actually I can show you right now. In my residual plot, odometer miles, your input is on the x here, and my residuals, which I'll show you what that is in a second, is on the y. And what that's showing us that how far we are observed from our prediction, and our prediction is going to be right here. And I'm going to back out and show you in a second what that means. Now, but I want to point out the way that I've plotted this residual plot is one of many ways to plot. There's multiple types of residual plots, but to me, this is the entry level, like, hey, this is what it is. If you can read one residual plot, you can read them all. You can dodge a wrench, you can dodge a ball. All right, so what is a residual? Residual, we think leftover. What's left over after something happens? So residual is your observed minus your predicted. It's just a subtraction, easy subtraction problem. So for example, if we had an observed vehicle price of 30,000, but we would have predicted it was 36,000. So 30 minus 36,000 gives us a residual of negative 6,000. So all of these residual, this y-axis shows us how far off we were from the actual. A residual of 0 means we were on point, we were on target. And like I said, the x-axis, which I'll get back to there in a second, the x-axis is the number of odometer miles. So you'll notice as the number of when the odometer miles are smaller, our residuals are smaller. And as the mileage increases on these vehicles, these residuals are way off. Some of them are, this one's close, but some of them are off. So that tells us a little bit of information. There's this concept of, when we predict, do we want to interpolate or extrapolate? And you've probably heard extrapolate. And extrapolate, we can use that in a lot of sentences and not even mean data. But extrapolating just means that we are predicting outside the model. So our model is based on these data points, if we wanted to predict for odometer miles way out here that's not in here, that's extrapolation. Interpolation would be predicting for vehicle miles, in this case, that are within our model, like basically between the odometer miles that I have here and here. Let's go back to the pizza. We saw that when we added the type of we changed the type of toppings, and we added in the extra, the $1.50 and the $1, we saw that it was still a linear model. It still had a high R-squared, but check this out. When I build out the residual plot, you'll see that our predictions are going to be way off as number of toppings increase. So why would you want to use a residual plot? Why does that matter if you already have R-squared? Well, what a residual plot's going to help you see is if there's any pattern. What's going on? Can I actually use this to predict? And I would say, well, yeah, if you might have an idea between 0 and 1 toppings, but as you go up in the number of toppings, your prediction can be way off. So if you're trying to, for example, predict the revenue or how much pizza you're going, or how much a pizza is going to be based on number of toppings alone, you can be very, very off. That's what this means. It was a lot harder to see with R-squared, but a residual plot will show you this. Also with prediction, you always have to ask, like, well, if I'm off, what does it matter? I mean, we're talking pizza prices here. Does it matter? Maybe not. So what I'm going to do is show you a little bit about how to create these calculations. And we're going to start off by putting odometer miles in columns, residuals in rows. But in order to do that, we have to calculate them. So this is our, like I said, residual plot. And how to calculate a residual, like I said, is your observed value minus your predicted. And let's see. So residual, here we go. I meant to not get away from that screen just yet. So predicted price is actually the big thing that we have to calculate right up here, because we don't have that in our data. Once we have the price of the vehicle, we can subtract off the predicted price. We have both of these. Then we can get the residual. So the big step here is actually finding the predicted price. You'll see that right here. So I'm going to go back to Tableau. Oh, actually, I do need to show you the formulas. You don't have to memorize this. There's no test at the end, and you could Google this if you wanted. It is really interesting to know that the calculation for slope, the slope of the line, that's as y increase, the rise over run, right? Y over x. This is the calculation. It's the R, as I told you earlier, see, it ties in, is correlation, the correlation coefficient, which we can actually calculate in Tableau very easily. And I'll show you the calculation. The correlation times, and you can put parentheses around this if it makes you happy, the standard deviation of the y's divided by the standard deviation of the x's. Two things that Tableau can also calculate. You don't have to go grab a TA84. You don't need it, just like I told my students. Then the y-intercept, intercept is where this line crosses this line, the y-axis. This is a calculation based on the average. This is the mean of the y's minus the slope, which you calculated here, times the mean of the x's. Okay, again, you don't need to know that except the first time you do this. And I did it for you. So I will pull up these calculations real fast for you. So starting with, you always start with slope, because you need slope for, and again, you'll be able to download this later, but you're going to need slope in order to do the y-intercept. So if you can see this, we have, this is where it was correlation times, and then that whole calculation, the standard deviation of the y's divided by the standard deviation of the x's. And if you're math brained like I am, it's like really cool to see this. Don't laugh. But I think it's really cool. This is where you can actually see in action that it's y over x, rise over run. That's where the y over x is. If you switch these two, the slope would be incorrect. So there is the slope calculation. And then we have to have our y-intercept calculation. So again, it's just the average of the y's minus the slope that you calculated times the average of the x's. That's the easy part. The hard part is telling Tableau that I need to now do this thing. And it's not that hard, I promise. I need to do this thing. That formula from algebra, when you say y equals mx plus b, to get your prediction, it comes from that line. The predicted price comes from the linear right here, this line, the line that the Tableau spits out for you. So it already knows what the line is. You just got to tell it to put those numbers in there. Unfortunately, this is the easiest way to do it. There's not another way to say, hey, give me the line from the regression. And the reason why is that line is created in your view. The trend line was created in your view, so it only understands your view. If you can't apply it into there without some level of detail telling it to hold it to the table, which is why we're going to do a table scoped level of detail calculation. So what all I have to do is to get the predicted value, which is why it's called y hat, y with a funny hat on it. That's why it's called y hat. Statisticians are not creative. They're names of things. So y hat, or the predicted y, is equal to your slope times x, sorry, that x value that you're plugging in, plus the intercept. I just realized I need to wrap up here in just a second. I apologize. I'll be really quick. So in order to do that here, that prediction, get that bigger here. We just have to tell it, use those cute little brackets there to help tell the calculation to use the slope and the y-intercept that was calculated for the whole table for every single value of x, okay? And then you can do this calculation. So you'll be able to pull that up on your own. I need to finish up here though, I just realized, sorry. All right, I like to talk, that's just what I do. So here you go. We have a residual plot from, there you go, from these calculations. And I thought I had a picture of it. I apologize. Here we go. And what it's telling us, as the number of odometers miles increases, the variation is a lot bigger as we go up. Meaning prediction for price is going to be a bit off as we go up in odometer miles. And we know that already. We actually know that because if you think common sense, well, if it has more miles, it's probably older. It has more things wrong with it. There's more variables to be impacting its price. Therefore, the prediction model is not going to be as accurate as you increase for odometer miles. As your odometer miles are lower, the prediction model can be pretty accurate, or at least a lot closer. All right, so closing up, just a few of those ideas I just wanted to recap for you. Trend lines, 2 reasons. Are you going to emphasize a relationship? Don't emphasize a relationship that's not there. Hey, I did a regression. Awesome. It doesn't tell you anything. I'm not chastising you, by the way, just giving you an idea. But we also want to use it to make predictions. Use R-squared as a sniff test to determine, is this predictable? So once the p-value is good, we just don't look at the p-value. We're looking at R-squared. Super important. But that's only part of the picture. We do want to look at the residual plot because we could have a high R-squared, but the residuals can tell us, yeah, but as the number of toppings increase, we have no predictability. So that's all I have for you today. I apologize, I went over a little bit. And if you have any questions, let me know.